So today we are going to look at a group of polynomial theorems, and our goal is to understand the rational root theorem, the polynomial remainder theorem, factor theorem, the fundamental theorem of algebra, and the various lemma attached to that. So we're looking at a bunch of different theorems. Our first up is this one. This is a formal statement of what we call the fundamental theorem of algebra. We're going to have a go at being able to read this statement. So if you see here, hold my pen. If you see here, we've got a function f of x, which is defined there. So this is how we define any possible polynomial. Any possible polynomial. Obviously, it's quite easy to generalize a second degree function. You can sort of say ax squared plus bx plus c, and that would define any second degree polynomial. But if we're trying to define a polynomial of the nth degree, then we're going to use a statement that looks something like this one. What we're doing mostly is we're using this symbol here in the center, the ellipsis, to say that there is an undetermined amount of expansion that can happen here at this particular point. We typically show the start of the pattern. So the first couple of terms shows how it starts. So we get a subscript n, x to the n. So that's the first term. So for instance, if we were to have a second degree, it would look something like this. Second degree might look like this. So in this particular case, n would be 2. It would be second degree. The nth term is a more general statement. an is the first term in the sequence, a subscript n. And then the second term is a subscript n minus 1. So whatever n is, we subtract 1, they'll cascade down all the way through until you get to the end, and then you'll get a2, a1, and a0. So our last term in the sequence is a0. In this particular case, this is a0. Here's a0. This one here, this would be a2, x to the 2. And then the middle term would be a1x to the 1. So it shows an expansion of any, it's a generalization. Side question for you. If this is any polynomial of the nth degree, how many terms will it have? Discuss with the person next to you. How many terms does this have? Second degree is here. How many terms does an nth degree have? Discuss with the people next to you. All right, let's hear your answers. How many terms does an nth degree polynomial have?
It has the amount of terms in the polynomial itself because it's going to be the highest degree. So like, let's say...
Did you give me an answer?
It depends.
No. If it's an nth degree polynomial, how many terms does it have? Andrew? N. No.
N plus 1.
N plus 1. N plus 1. That's why this last term here is a0. If we count from 0 to n, we're counting n plus 1 terms. If we're counting from 0 to 5, we're counting 6 numbers. We're counting from 0 to 5, 0, 1, 2, 3, 4, 6 terms. So there's always n plus 1 terms in an nth degree polynomial. So that's our first bit. What it also says, you've got to get used to reading these type of bits at the end of the definition. So it says that any nth degree polynomial can be expressed like this, but an cannot be 0. An is the lead coefficient. We know it is the lead coefficient. Why can the lead coefficient not be 0?
Because that means a would have to be 1 every time?
Nope. Why can the lead coefficient not be 0?
Because if you have n terms and the lead coefficient of your n term is like 0, then you don't have n terms, you have n minus 1 terms.
Okay. Yeah. Well, if it was an nth degree polynomial and an is 0, then it's not an nth degree polynomial. It's an n minus 1th degree polynomial. It would You make the first term in a quadratic 0, you've not got a quadratic, you've got a linear. But you can make any of the other ones 0, it's not a problem after that. So that's what this is. It says it's going to have real or complex coefficients. So that means in this particular case, these numbers could be real numbers or they could be complex numbers. Some of these definitions are going to move backwards and forwards between the concept of real and complex numbers. So complex numbers includes imaginary numbers, which we will look at a little bit later. So if we have any polynomial, so this is what it says. It says if we have any polynomial, it has at least one 0. It has at least one 0. You cannot get a polynomial that doesn't have a 0. Now, you can get polynomials that have no real roots. So if a second degree function has no real roots, what type of roots does it have? Let me take somebody else. If a second degree function, polynomial has no real roots, what type of roots does it have?
Complex roots.
Complex roots. Complex roots. So a second degree polynomial is always going to have 2 roots, including multiplicities, 2 complex roots, including multiplicities. So that's what that says. It says it has to have at least one. It has to have at least one. It says there is an omega, this little symbol here, is the Greek letter omega. It's the lowercase version of this symbol, omega. So it says that omega is an element of the set of complex numbers. So it says because it has one root, it has to have one root, that root would be omega. There has to be a root such that f of omega is equal to 0, because it's a 0.
But is it saying that the root has to be complex or it can be?
All numbers are complex. So 5 is a complex number. All real and imaginary numbers are complex. All combinations of real and imaginary numbers are complex. So 0 is a complex number. Doesn't seem very complex. Okay, from the fundamental theorem of algebra, we can derive this lemma, a helping theorem. So when it comes to proving the fundamental theorem of algebra, generally you would prove this theorem first, this lemma, and then use this lemma to prove the fundamental theorem of algebra. So let's have a read through the lemma. It says that each polynomial, this is a polynomial, so it's the same definition that we've just had, with real coefficients. So look, it says here with real or complex coefficients. This one specifies that they must be real coefficients. They must be real coefficients. So any polynomial with real coefficients, and we'll see why it says real in a bit, can be written in factor form, like this. So we can factor it. So you can take any polynomial that we saw last week and you can factor it out like that. We had a couple, so we had some last week that we were looking at, and we factored them to things that look like this. So we were factoring quadratics and things, and sometimes they would look like this. Is this in the form written here above in the lemma? Is it written in the correct form? Discuss with the person next to you.
If we're looking at only one lemma,
that form.
So what does omega mean?
It's a Greek letter. You know how we like to use specific letters for certain things, x, y, and z for variables, f for functions. So in this theorem, we will use omega to mean a root.
And omega in this is a complex.
Yes, it tells you.
I think it just means that A is the coefficient of the degree of the
So that is not in that formula because -5 and 1 aren't complex.
Yeah, they are.
They are? 5 is the coefficient for that degree. So it just says 5 and then something. 5, 2 under.
So but if it's like omega squared,
Sorry, this is the coefficient for the square.
-5 cannot be a square.
Yeah.
Like here you put 2x minus 5 and it's like x minus omega squared. But 5 can't like be a root.
Okay. It's not 5, it's
-5.
no, it's 2.5. Okay. Is this written in this format? No. Why not? Look at the format. Does it have? Do any of the x's have a 2 in front of them?
No.
Can we write it in that format?
Yes.
How would we do it?
Would you make it x minus 5 and x plus 5?
No.
But then what
That
would
would
you
change it.
But then what would you do with that?
You take just you factor it out.
Okay, so we factor out the 2. Now it's in that form.
Yes.
Now it's in that form. And it says that it says here in this one that the roots are omega. So omega 1 is 5 over 2. Omega 2 is -1. Omega 2 is -1. Omega 1 is 5 over 2. Keep your signs right. Notice the format says it should be minus. So you don't have to factor out the minus. It is technically correct. But in our understanding, we can see the roots clearly, like this now. We can see the roots are 5 over 2 and -1. We don't have to write it like this. We can write it like that, and it's still in that format. We can understand it. So it says that any polynomial can be written out as in this sort of product of linear factors. It can be written out as a product of linear factors like this one. So once you find your root, it means you can write it in this format and it's going to be correct. So, discuss with the person next to you this question. How many solutions do these equations have? How many solutions do the equations have? So this first one, there's a few ways. We can enter into the discriminant. I mean, we can use the discriminant b squared minus 4ac. That's going to give us 9. So if the discriminant is bigger than 0, it implies 2 real solutions. The second one, we can clearly see here what is the solution? We can see instantly here, hopefully, that's the solution. And there's no other solutions. This implies 1 real solution. Likewise for this third one, we don't have to expand it and put it into the discriminant. We just rearrange this one to here. And we see that this is going to be -4. You can't find the square root of a negative number. This means there's no real solutions. We might say, in this terms, when it comes to solving equations, this is how many solutions there are to the equation. So we can find 2 numbers that will work for this, We can find one number that will work for that, and we can't find a real number that will work for this one and balance the equation. Now, when it comes to use of the fundamental theorem of algebra, we're looking for the number of complex roots, including any repeated roots. So for instance, if we were working with a function like this one here, 3x squared, we would often say that it has, if we were to take the function f of x is equal to 3x, and we want to know how many roots this has, how many complex roots it has, we could say it has the root x equal to 0, and that root has a multiplicity of 2, meaning it occurs twice. It would be a double root. We would say multiplicity of 2. That is a repeated root. So in this particular example, when it's saying including repeated roots, so let's say this equation has a variety of roots and they're all identical. That's possible. In that particular case, you would say that that root has a multiplicity of 3. So, according to the fundamental theorem of algebra, how many roots will it have? Well, the fundamental theorem of algebra says that we can take any polynomial, this would be a third-degree polynomial, and we would express it as 3 factors, meaning 3 roots. So, this one is going, including repeated roots, is going to have 3. Including repeated roots, it's going to have 3 roots. We have to read the wording very carefully to see what it's talking about.
But how do you know if all those 3 are complex? Because we know there's 3 roots, but some...
Real numbers are complex as
Oh.
well. Real numbers are complex as well. So in the next one, find the number of complex roots, including repeated roots, of a 6th degree polynomial with complex coefficients. So how many complex roots, including repeated roots, would a 6th degree have?
6.
6. Easier than...
That's simple.
Alright, so next we're going into the rational root theorem. So the rational root theorem is giving a polynomial. So we have a polynomial here, nth degree polynomial, just general format. We can write it in factor form. We've seen these two before. And just take care of what we're talking about here and things, is we are going to have n roots. We're always going to have n roots. We can see that here, because n iterates from 1 up, sorry, k iterates up from 1 to n, meaning there'll be n possible k's. So the subscript, omega k, where omega k is a complex number, and k is the integers from 1 to n, meaning there'll be n roots to an nth polynomial in factor form. That means we already know that. So far what I'm reading there is information that we've seen on the last two. Because this last sentence we have to read carefully for the rational root theory. So a rational zero. So what is a rational zero? Let's have a look at numbers a little bit. So just as a number diagram some of you guys are having trouble with. Here in the center of our number diagram, we have numbers of this type. What type of numbers are these? What's this symbol mean? This is integers. Integers. So here in the center we have the set of integers. Around the set of integers, we have this set. Let me write an example. This set, around the set of integers, are the rational numbers. The rational numbers are numbers that can be written in the form of a over b, where a and b are integers, and b is not a factor of a. So, like a half. Does this mean that whole numbers are also fractions?
Yeah.
Yes. So how would we express 5 as a fraction?
5/1.
5/1. So whole numbers are also rational numbers. And then around this set of rational numbers comes the next set, real numbers. Who can give me an example of a number that is real but not rational? Pi, perfect. Pi is a number that is real or not rational. If it's not rational, what is it?
Irrational.
Irrational. If you wanted to specify irrational numbers, they could go in this set here. No, they couldn't. Because they're mutually exclusive to the other one. So the set of irrational numbers doesn't have its own symbol.
Root.
We use the rational symbols, then we use the complement symbol. Complement means not rational. That's the complement symbol. You should have seen the complement symbol when you did sets last year. The complement symbol. That's not good. Not a big issue. The next set is the set of complex numbers. Is 1 a complex number?
Yes.
Is a half? Is pi?
Yes.
What is a complex number but not real? What is it?
Root.
What is a complex? No, they're irrational. Unless, well, depending on what. Many of them are irrational. Not all. I. So the complex number I would be an example. This is an imaginary number. Or you could have the number 2 plus 3i, and this one is complex. Real, imaginary, complex. So the reason it can be, so a complex number is of the form a plus bi. And the reason that 1 can be a complex number is it's 1 plus 0i. The reason that I can be a complex number is it's 0 plus I. That's the sets of numbers.
So,
Yes.
isn't pi an irrational number?
Yes.
Then why is it in the rational section?
It's rational. It's real numbers, that one.
Oh.
Real but not rational.
Oh.
So here are the set of rational numbers. Now that's what we're looking at. That's what we're looking at. We are looking at a rational 0 of a polynomial is in the fact form b over q, where p, and this is the new bit, p is a factor of a0, the constant at the end. Q is a factor of a, the number at the front. So anything that can be written in this form, and going back to my example, I did an example a bit like this. Here. So let me come back to this one. So we led in with this one, 2x minus 5x plus 1. And I said that we could write this one as 2 bracket x minus 5 over 2 bracket x minus negative 1. So the rational zeros of this one is 5 over 2 and negative 1. The rational zeros of this is 5 over 2 and negative 1. If we were to expand this, we're going to get 2x squared plus dot dot dot, I'm being lazy, don't have to do the bit in the middle, plus negative 5 minus 5. So expanding this expression, we can see this, I don't need the middle term, I need the first term and the last term, so I can use the ellipsis notation here just to be lazy. And what it means is, what are our roots? Our roots are negative 5, 2, this is omega 1, and omega 2 is equal to negative 1. So these are the rational roots of this polynomial. We can see it here particularly. You can see that the roots are these two. These are the rational roots. How do these two roots relate to these two numbers? Let's take, for instance, omega 1. Let's take omega 1. Omega 1 is minus 5 over 2. It says here that p is a factor of a0. What it means is it's saying that -5 is a factor of this term here at the end. And we see that. We can see that very clearly. The next part says q is a factor of an, this number here at the front. We can see that. That is what this is telling us. This is the rational root theorem. So, let's have a go at this question. Let's have a go at this question. Read it to yourself to begin with. I'm going to go through it, but read it to yourself. You have to be able to read which words are we struggling with. So we have a polynomial function, hx, with integer coefficients, and it has a leading coefficient of 7 and a constant term of 9. So what does this polynomial look like? From this first sentence, we can say that h of x is equal to 7x to the n plus ... and a constant of 9. So that first sentence says the polynomial h of x with integer coefficients has a leading coefficient of 7 and a constant term of 9. That first sentence tells us this much information. According to the rational root theorem, which of the following are possible roots? Which of the following are possible roots? So let's go back to the rational root theorem. P over Q, P is a factor of A0. Q is a factor of AN. So, P over Q, P is a factor of A0. Q is a factor of AN. So P is a factor of the constant, Q is a factor of the lead coefficient. So the factors of the constant, what are the factors of 9? 1, 3, 9. Any more?
No.
What about -1, -3, -9?
Oh yeah.
This is possible too, isn't it?
Mm-hmm.
Yeah. So, do we have any of those? Yeah? Okay, so what are the factors of 7?
1 and 7.
The factors of this are 1, 7, -1, -7. So if Q is one of these, that means it's possible to have anything of the form P over 1, like these two. Is it valid? Or P over 7. Do we have anything of the form P over 7?
Yes.
Yeah.
This one. Oops. Oh, green. This one. Could this be a possible root?
Yeah.
Yes.
Why?
Because it's over.
It's not a factor of.
Yeah, it's not a factor of
No.
A or
It could. So first up was, yeah, it can be 7 over 1. Is 7 a factor of 9?
No.
It can't be. It can't be. 7 is not a factor of 9. It can't be that one. So,
Does that mean that it's 9 because you can't have the fraction as a...
in this question, we don't know the degree of the polynomial. We don't know the degree, which means we don't know how many roots it's going to have. But we do know the lead coefficient and the last term. From that, it tells us that 9 minus 3 and 1 over 7 could be roots. Could be roots. It doesn't tell us that they are. We don't have enough information to know what the actual roots are, but it does mean that these could be possible roots. It also tells us that so many other numbers definitely can't be. There are so many numbers that can't be roots. We know that 7 is not a root, 5 is not a root, 4 is not a root, any even number is not going to be a root.
Negative numbers. Also negative numbers, right?
No, negative numbers can be. Negative numbers can be. But we basically take these 6 numbers and these 4 numbers, put them into this combination, and those are all the possible permutations of what roots could be. So it's a finite number, if we're just guessing what the roots are. Have a go at this question.
So there's only possible answers, there's no specific correct answer?
At the moment, they're possible answers.
Unless they tell us the leading coefficient, right?
No, they told us the lead coefficient. We can't see whether they are or not unless we see the whole polynomial. We can't. But it's basically a theorem that's giving us where to start looking. Start looking here. One of these might be.
And it's like more of saying which one isn't, right?
It says it helps you throw out hundreds.
Yeah.
Yeah.
What time does this class end? 10:40?
Well, we understand that all of it.
Okay, so h of x is going to be minus 1x to the n plus, minus 20. We can see this. So the factors of q are going to be 1 or minus 1. The factors of p are going to be 1, 2, 4, 5, 10, 20.
And negative 1, negative 2.
And negatives. So, can negative a quarter be a possible root? No. Negative quarter cannot be.
But isn't it P over Q where P is supposed to be factor of?
Yeah, but P is the constant one or negative. Yeah. Oh, okay. It can't be also one.
It can't be the second one either, right?
Can't be the second one? What about the other ones?
Yeah.
These could be roots. These could be roots. Now, what are we going to do with the roots once we guess that it could be those ones? What are we going to do with the roots once we guess? These are the most important two. These two theorems are the most important two. We're going to use these ones the most. Let's try and refocus on this bit now. So, polynomial remainder theorem. So given any polynomial, if you divide the polynomial, f of x, by the linear factor x minus a, then the remainder will be the same as a. 1. Okay, let's go back to last week and test this out. Last week we did some polynomial division, like this one. We did some polynomial here, division. What it's saying is, so we've got this polynomial here. We've got this polynomial here. And we know we have this, we're dividing by x minus 1. So what is the value of a?
Negative.
Let's go back and read the theorem carefully. Is it 1 or negative 1? What is the value of a?
1.
Can we see there in the theorem that a is 1?
Yeah.
Yes.
So what this theorem here tells us is it's saying that f of 1 is going to be 5. Let's try it. Let's try it. Let's try f. No? Okay. F of 1. So we want 5, 1 cubed minus 1 squared plus 0, 1 plus 1. That is going to give us 5 minus 1 plus 0 plus 1 gives us 5. F of 1 is 5. Let's try another one. Try this one.
Does that mean it's 2?
3. So we divide, you put f
F of 3 should equal what?
5.
Should we try it? Let's try f of 3. 2 bracket 3 cubed minus 3 bracket 3 squared minus 14 bracket 3 minus 5. So this is what's 3? Plus 20. Plus 20 equals to minus 1. Yeah. Plus 20 equals 5. We stick this into our calculator. Try it on your calculator. Verify that it works.
Oh yeah, sure. Are we going to have to start bringing our graphing calculator?
Every class. Should be on your desk every class. Okay, so you're sticking it into your calculator, you should fairly quickly see that is true. Two times 3 cubed minus 3 times 9 minus 14 minus 3 plus 7. Okay, so that's polynomial remainder theorem. There is another theorem similar to this one. It says that, and it's basically a lemma from the polynomial remainder theorem. So if x minus a is a factor, from the fundamental theorem of algebra, that tells us that a is a root. If x minus a is a linear factor, it tells us that a is a root. So in this particular one, the factor theorem tells us that any polynomial, f of a is going to be 0. There'll be no remainder when you divide by a factor which has a root in it, like this one. So this one's really useful for us. We can use factor theorem and the fundamental theorem of algebra and polynomial remainder theorem to find roots quickly for higher degree polynomials.
So it's saying if the remainder is 0,
Then it's a if f of a is equal to, then it is a factor. Yeah.
What's the
It means we can factor it out. Let me explain this one a little bit more. So if we have a polynomial like this one, f of x, and f of a is equal to 0, then it means that a must be a factor. That means we can rewrite this as x minus a bracket q of x, and there'll be no remainder. It means we can factor it out. What will be the degree of q? What will be the degree of q?
Wait,
What is the degree of f?
it could be n.
So the degree of the function f is equal to n. The degree of the function q,
N minus 1.
n minus 1. I'm going to tie all these together in a second.
Wait, what's that? What did you write?
Why should I wait?
QG.
Why should I wait?
No, D, and then the Q and
Degree. That's the degree function. It tells you the degree of a polynomial.
I got it too.
It's an f. Degree of f is n. The degree of q is n minus 1.
I don't know if it's certain. But what does the complement word for once in a sentence? Because you said it once and then I want to write it.
Given any polynomial, if f of a is equal to 0, then x minus a is a factor. And it's inwards.
It just makes sense what you say.
Alright. Find the remainder when we divide this by that. Shall we use the polynomial division?
We could.
I
don't think.
Is there a quicker way than using the...
Yes,
The factor theory.
No.
The polynomial remainder theorem.
To find the remainder, what do we use? Factor theorem or remainder theorem? What does remainder theorem tell us to do? We want to find the remainder. How do we find the remainder?
We put minus 2 as f.
We find f of
Negative.
-2. So that is going to be 2 bracket -2 cubed plus 6 bracket -2 squared minus 4. So -2 cubed, is that 8 or minus 8? So this is minus 16. 2 minus 2 squared, is that 4? 6 times 4?
It's positive.
24 minus 4. If we were to do the polynomial division on this, we would get 4.
Why is it negative 2 again?
Because it's all, if we look to the theorem, it should always be written in the form of x minus a. That's something you got familiar with back in IM3 when you just started factoring quadratics. You can see that the solutions to the equation is always, you're changing the sign always, because in fundamental theorem of algebra, it's always x minus the root is the correct generalized form. So, if we're trying to find the remainder when this is divided by x plus 2, the remainder is going to be 4. It tells us that f of x is going to be able to be factored into g of x times q of x plus 4. We have a problem-solving question now. So we've got a polynomial. One of the coefficients isn't given to us. Given that f of x has a factor x minus a, find the value of a. Which theorem should we use for this? Factor theorem? Let's go back and look at factor theorem again. Factor theorem is this one. So it says that f of a is equal to 0, so f of the root is equal to 0 if x minus the root is a factor. So in this question we're told that x minus 4 is a factor. So f of which number is equal to 0?
4.
F of 4 is equal to 0. The information here, given that it has a factor x minus 4, so let me just highlight that. This clause tells us this from factor theorem. So if x minus 4 is a factor, it tells us f of 4 must be 0. We could therefore use this to create an equation to solve our problem. So we'll take our polynomial. We know that f of 4 is going to be 3 bracket 4 cubed minus 11 bracket 4 squared plus 4a plus 8. Therefore, this has to equal 0. If we collect together all of the numbers, what do we get? Use your calculator if you want. Use your calculator to collect together the numbers. So we want 3 times 4 cubed minus 11 times 16 plus 8. 24. So 4a equals negative 24. A is negative 6. I'll give you a minute to discuss that.
Why is it because you subtracted 24. Because like 3 is all the way.
Yeah, that's why I think switching is
With the remainder.
Here it's just saying it's divided. It doesn't tell you that x plus 2 is a factor. That's the key difference. You get a remainder when you do the division. But on this one, you're told that this is a factor. The remainder will be 0. Last one. Last one. Last question. Then you have some time to work through some problems. So we need to solve this equation. Actually, I got one more thing as well. We want to solve this equation. Sorry. I think before we solve this equation, I'll circle back. I'll do the other thing first. Last week we looked at polynomial division, and we worked with problems like this one. So, with this question, we said when we divided, we divided this expression by this one, and we got this as the quotient, and this is the remainder. Just remove the. Okay. So last week we looked at polynomial division, which is a useful technique and will always work when you're dividing polynomials. Always going to work. There is a shortcut to polynomial division called synthetic division. Synthetic division won't always work, but it will work for a linear factor. It will work for a linear factor. Only use this one where you have a root or your a value is a whole number. Only use it when a is a whole number. When it's not, don't use this technique. But when you use this technique, it can be really quick. I'm going to show you how to do it. So what we do is we take the polynomial and we take off the coefficients. So I'm just going to do a couple of examples. So this is called synthetic division, or Horner's algorithm. Take your coefficients, 2, minus 3, minus 14, 20. Take the value of a. What is the value of a in this factor x minus 3? A is 3, like this. So drop the first coefficient down, all the way, like that one. Then take this coefficient and multiply it by that one. Take this. Take a, which is 3, multiplied by the 2, we get a 6. Add these two together. This is going to be an addition. Add them together. Minus 3 plus 6, 3. Take this 3 multiplied by that one. Add these two together.
Minus 5.
Minus 5. 3 times
15.
minus 15. Add them together. 5.
15.
So, when you do that division, you're going to get 2x squared, we're going to need x squared because it's 3 terms, plus 3x minus 5, remainder 5. And that is the result we got here.
So you could divide into 3 on the left side, but where did you get out first?
2 minus 3 minus 14, 20.
Yeah, so you
Multiply.
This one?
no, the one
Minus
That one?
plus 6
Drop it down.
3 times 3 is
Drop
9.
it down. Sorry, we're going to do some. We're going to do a couple of these.
Negative. Just like jump around.
Try.
Keep grading people, jump back.
But what a negative 5
Let's try this one. So which coefficient? Follow it along with me. Follow it along with me, and then I'll give you one for you to do. Which coefficients are we going to use? 5, negative 1,
and 1.
no,
And then the remainder is 1.
0,
Remainder
1. Okay. What value of a shall we use?
1.
1. What do we do first?
Bring the 5 down.
Bring the 5 down. Next.
1 times 5 is 5.
1 times 5 is 5. And then what?
4.
How do we get 4?
You
Minus 1 plus 5.
Add.
Minus 1 plus 5.
Add. So this gives us 4. Then what do we do?
You got 4 plus 4.
1 times 4.
4.
Then we add these.
4.
1 times 4 again.
4. So you get 5. Which is remainder 5.
What is the quotient?
5x cubed
5
plus 4 and
There's 3 terms, so it's going to be 5x squared
plus 4x
plus 4x
plus 4.
plus 4, remainder 5. And it's 5x, 4. Try one for yourself.
So is there always a remainder? Like how do you know it's
No,
remainder?
not if it's a factor, it would be remainder 0. So
But if you add them in
if you're dividing by x minus a and a is a factor, you get remainder 0. Pop out 0 here. Right. Try do this one for yourself using synthetic division.
Which scenario does this synthetic division work?
When you've got x minus a and a is an integer.
Integer means no.
Whole number.
Integer means no.
Whole number.
So if it's x squared.
squared, when you're dividing by a linear.
So if it's x squared, so
Like
it's
zero? Until like 100 as in number.
It's a number, it's not a polynomial. There's no letters, it's a number.
But can you use this to dividing by x squared? But that's
No.
not gonna be a.
There are tricks when you're dividing by x squared. So if you're, don't use synthetic division when you're dividing by a non-linear factor.
Yeah.
It only works for linear factors. And there is a shortcut and a trick that you can do when it's a rational root. Let's say it's x minus a third or x minus 2 over 5. Yeah. When it's something like that, don't do it. Do it for simple ones when it's x minus an integer.
But if a is a whole number, do you mean x minus
Integer.
a or the ax squared thing?
X minus a. Most questions. Most questions.
We just did that.
No?
Oh yeah, we did do this.
Okay. Do this one.
Sir, are you gonna post this up on your YouTube today?
Yes.
What time do you think?
This is the host. This is the host.
10:40?
Oh, you posted early.
It's just the whole house.
I thought you posted at like 9.
No, I'll post it on my YouTube at the end of class.
Oh,
I'll put it onto the Google Classroom when I get a chance. Okay. Did we get our answer?
No. So when you put minus 2.
Why don't we put pencil in
Yeah, I think you put minus 2.
Why are you doing that? You should practice this.
Yeah,
Right.
yeah, he's helping us. So that is it. But sir, it will only work if the leading coefficients are not number. Because he said if there's no whole number, you can't do it.
If your divisor here is x minus a, where a is an integer. X minus a is an integer. Do this. Doesn't matter what the polynomial is. Any polynomial. As long as it's real coefficients.
If you find out like
No.
amazing.
So it's just like an actual way to do it. So that that's if you ever need to rush, you can do it.
Okay, let's have a look. We should have the numbers 3, 8, 6, 11. We are going to divide by what? Sorry, what's our minus 2? What do we do first? Bring the 3 down. What do we get? If we add them,
Plus.
what do we get? Add them, multiply, add them.
Remainder 7.
So this is 3x squared plus 2x plus 2, remainder 7. Alright, you get the idea of synthetic division? Hopefully you can practice that with some of the problems that we're working with. Let me go on to our last problem. We've got 10 minutes for this one. View browser. Okay, we need to solve this equation. That means we need to factor it. We can't factor third, pay attention on this one. Pay attention. We can't factor a third degree function. We haven't got the techniques for that. In fact, if you have the knowledge from this lesson in the 15th century, you could have made yourself a rich man. In Italy at this time in the 16th century, during the Renaissance, they used to have competitions with large amounts of money available for the winner who could solve the problem quickest, and it was solving third degree equations like this one, as they were trying to come up with, because they had the quadratic formula at that point, and they were trying to come up with a formula for third degrees. There is a formula. It's a Cardoso's theorem, I think. There is a formula. It's complicated and tricky to use. You can use this technique. Anyway, we want to try and find the solutions to this equation. We are going to use one of the theorems to guess possible roots. Now, which theorem do we use to guess roots?
The rational root theorem.
Rational root theorem. We're going to use rational root theorem here first to guess a root. What could be a possible root?
3.
3?
Wait.
What are the factors of 45?
It can be
1,
5,
5, 3,
2?
no, 3, 5.
9.
No.
15.
9?
Yeah.
Yeah, sorry, it's 9. 15, 45.
And then the negatives.
And then
2, which is 1 and 2.
1 over 2. Well, it doesn't have to be 1 over 2 as the and 1 over 1. It could also be 5 over 2.
Is it because it's 2.5?
No, because 5 is a factor of this and 2 is a factor of that. So 5 over 2 is 8 over
5 over 1.
There's lots, 9 over 2.
Can be over.
So there's a whole bunch. We are math students, so we are smart. We will use the easiest one first until we find one that works. Now, next up we are going to use factor theorem because we want it to be a factor. Now, which of factor theorem tells us that f of a is equal to 0? If it tells us the other way around actually. It says if f of a is equal to 0, it also implies that x minus a is a factor. Let's go back to factor theorem. Factor theorem says that if f of a is 0, then x minus a is a factor. So we've got a list now of possible factors, and we need to put them into the function until we get a 0. Now, who wants to put 5 over 2 into this? No. And who wants to put 1 into this? No. We're going to start with 1, aren't we? Because it's the easiest one. Start where it's easiest. 1, negative 1. Then 2, negative 2. And so on. Unless you see something that's going to cause it to cancel. But pretty much I'm going to start here. What is f of 1? F of 1 is 2 minus 5 minus 18 plus 45. Is that equal to 0? You don't have to add it all up. Look, that's about 20. And that has to cancel the 45. That one's not going to work.
No.
Is the minus 1 going to work?
No.
The minus 1 is going to probably not work. You can see that one. So that's going to give us negative 2
Plus 5.
plus 5
Plus 18.
plus 18.
Minus 45.
No, plus 45. Still too big. Let's try the 3. Let's try the 3. F of 3. What's it going to give us here? It's going to give us 8. 2 8s are 16. Here it's going to give us 3 squared is how much? 9. 9 times 5?
45.
So minus 45? Sorry, I did.
Sorry, that's
I did the math there. 3 squared was 9, 290.
No, it's 3
no,
cubed.
it's 3 for you.
It's supposed to be 54.
27. 27.
Sorry, I'm getting tired. Let's go to I'm making mistakes. If I'm making mistakes, it's because I'm jumping. So let's stop jumping a little bit. Let's write it. Take a little bit longer to write it. We've got 2 bracket 3 cubed minus 5 bracket 3 squared minus 18 bracket 3 plus 45. And this is going to give us 3 cubed is 27
Times 2.
54. 3 squared? times 5
-45.
minus 45. 18 times 3.
Minus 54.
I do it like this. 3 times 10. 3 times 8. Add them together. Minus 54.
That's gonna work.
Yeah.
That's 45.
What does this imply?
That 3 is a 0. So
This is
the factor is x minus 3.
okay. So we have found a factor for the polynomial now. We have successfully found a factor. We need to solve the equation. So let's factor this out. Let's use synthetic division to factor it out. So using synthetic division now to factor it out, we are going, I'm just going to do this in red. So we've got 2, negative 5, negative 18, 45. We are pulling out 3. So what do I do? What do we do first?
Bring down the 2.
Bring down the 2. Then what?
Multiply. 3 times 2 is 6.
Put it here. Then what?
One.
Sorry, I just want to slow it down a little bit so that everybody's following. Then we add these together. What do we get?
1.
1. Now what do we do?
Multiply 1 and 3.
So 3.
Negative 6.
Minus 15.
Negative 15.
This will give us
Negative 15.
sorry, negative 15.
Then you put the minus 45 up here. So we'll get 0 remainder.
We already knew we were going to get 0.
Yes.
But that's a good verification that I haven't messed up.
Yes, sir.
If I'd messed up this algorithm, it would show me there, because I know that this has to come out as a 0. Useful. So this gives us the polynomial now in factored form. So we've got our polynomial is f of x. We know that f of x is equal to x minus 3 bracket 2x squared plus x minus 15. Can we factor that quadratic?
Yes.
Have a go at factoring that quadratic, and then we'll have our solutions to the equation.
So 8 times c, so you do 8 times
Да, у меня теперь вот такая вот панорама на все это получается в этом банке.
Adds up to 1. Then this no.
Yeah, but you don't have to put the factors, you just put
Okay, so if you complete factoring here, you'll find this as your solutions, and these are the solutions to the problem. Okay, just finishing off there is a homework exercise for us today. I've given you answers to 3 of the questions. No. For practice, if you want, I've shared it with you. I like them to be smaller than large.
How